Binarization of level information. In order to binarize level information, the codeword is assigned as follows. Given a particular parameter k, an absolute transform coefficient to be coded consists of prefix part and a suffix part. The prefix is coded using a truncated unary code and the suffix is coded using a variable length code, as shown in Table 4. As shown in Table 4, the length of the variable length code depends on the unary code and the parameter k. That is, the parameter k controls the length of the codeword structure. Table 5 shows the binarization of coef_abs_level_remaining when the parameter k is equal to 1. Binarization method for level information. Example of binarization for level information when k equals 1. The update of the parameter based on the magnitude of the previously encoded absolute level value. After encode one level value, the update mechanism is conducted, as shown in 1. Here, sh indicates the previously encoded level value, k is the parameter, and k is the updated parameter. The parameter k ranged from 0 to 4. Based on the pseudocode, we can summarize the selected parameter according to the absolute level range. Absolute level range for determining the parameter. In level information coding, the absolute value of each non-zero coefficient is adaptively encoded by a codeword structure with the selected parameter k. The codeword with certain parameter is designed to encode efficiently in a specified range of the absolute level, as described in Table 6. We can note that the parameter monotonically increases according to the previously encoded absolute level. That is because level coding in CABIC is based on the expectation that absolute level is likely to increase at low frequencies. Efficient differential pixel value coding. In this section, we introduce an efficient differential pixel value coding method. The proposed method consists of two parts, mode-dependent differential pixel scanning and level information coding with modified binarization. In the HEVC scanning method, the horizontal scan is used for a vertically predicted block. In the similar way, for a horizontally predicted block, the vertical scan is used. Undoubtedly, SAP significantly improves coding efficiency of interprediction and lossless coding. However, since the current sample cannot exactly predicted by reference samples and there is no transform and quantization processes, correlation in the prediction direction still remains. Thus, the conventional scanning index mapping in HEVC cannot provide the best coding performance for lossless video coding. In lossless coding, interpredicted residuals do not show the same behavior as transformed coefficients. Instead, it is observed that for relatively small 2, for example an 8x8 or a 4x4 2, when interprediction is in vertical direction, the residual will often appear in vertical direction. Thus, a vertical scan will often result in better performance. Similarly, when the interprediction is in horizontal direction, a horizontal scan will often be better. It is motivation of MDRS and we follow this observation. We assign the vertical scanning pattern to the vertically predicted block and the horizontal pattern to the horizontally predicted block. However, MDRS is proposed for the HEVC test model, HOME 4.0 and the current HEVC standard uses the different interprediction mode number. Hence, we change the scan index selection to fit the current HEVC interprediction mode number, as shown in Table 7. Modified lookup table for the scan index selection. In lossless coding, these differential pixel values are likely to be the end of the poo. As mentioned in Section 2, padded samples are produced and used as reference samples in the prediction process. Shows an example that a padded sample is used as reference sample. Here, the padded samples are copied from the closest neighboring sample S. Strictly speaking, these padded samples are not actual neighboring samples of the current sample X, and samples that uses these padded samples as reference samples might provide poor prediction performance. It results in the increase of the residual data. Two types of padded samples in the sample-based angular prediction. Since syntax elements in the entropy coder are encoded in the reverse order, the beginning part of the scanned coefficient sequence has a higher probability of having non-zero coefficients compared with the ending part. In this way, the resultant scan sequence is more suitable for the entropy coding method and experimental results verify that considerable bit saving is achieved. Thus, we change the scan order. For each scanning pattern, we change the scan order in the opposite order of the conventional scanning method. As mentioned, in lossless coding, The residual data is the differential pixel values between the original and the predicted pixel values without transform and quantization. Main difference between differential pixel values in lossless coding and quantization transform coefficients of lossy coding is the magnitude of the level information. Shows the magnitude distribution of coef_abs_level_ remaining in lossy and lossless coding. We can observe that differential pixel values have much bigger level information than quantized transform coefficients in lossy coding. In other words, differential pixel values have a wide range of magnitudes. Hence, in our binarization, we extend the parameter range from 0 to 6. The parameter is initially set to 0. The parameter monotonically increases based on 2. It contributes the coding performance of the proposed method since it provides appropriate binarization code for bigger level values. The construction method of Codeword is same with conventional HEVC coding, as described in section 2. Magnitude distribution of coef_abs_level_remaining.